So welcome back. So in the previous module, we looked at this typical machine learning, supervised machine learning setup. And the key there was to now come up with an algorithm for learning the parameters, right? So what we'll do is now start with an infeasible algorithm, right, which will not really work in practice, but it will give us intuitions about what should we do to make it, go towards the more practical approach, right? So let's start. So this is the supervised machine learning setup that I have. I have n inputs, okay, and I have some weights, and then I have the output. Now this is the model, right? This is my approximation of the relation between y and x, right? So this is f hat actually. This is the model, and now I want to know an algorithm, okay, which can be used to learn the parameters of this model, given the data that would be given to me, and using some objective function which makes sense. Right? So that's what my quest is. Okay. Now, and this is what my f hat of x is. I'll generally use f of x, right? I mean, I've explained the difference between f of x and f hat of x, but I'll just call it f of x. And from the context, it should be clear that I'm talking about my approximation, because the true function, of course, is not known, right? So I cannot even define that, right? And I'll use sigma here, which is written here, is actually a short form or the notation for the sigmoid function. Okay. So now we'll consider a very simplified version of this model, right? For all our explanation, that there's only one input which is connected by the weight w, and then there's this constantly on input which was connected by minus w naught. But now, to be consistent with the literature, going forward, we are going to call it as b, right? And b stands for bias. So instead of w naught, we're going to use b, and our function would then become minus of wx plus b. Earlier it was minus of wx plus w naught, right? So you're just changing that notation, and I'll stick to this notation for the rest of the course now, right? Yeah. And lastly, right, so far what we have been doing is we have been trying to talk about the problem that you are given one input and you're trying to predict the value of the 0 or 1, right, whether this movie are going to like it or not. But now I'm going to make it a problem where you're trying to predict a real value instead of a Boolean value, and you're trying to predict the IMDb rating on a scale of 0 to 1, right? So it could take values like 0, 0.05, 0.1, 0.2, whatever, right? It could take any of these values. So it's a real input, a real output, right? So that's it's easier for me to explain a few things in this setup, but it does not change anything that I'm going to talk about. Even if you had Boolean inputs, we'll see later on how to adjust the same explanation to Boolean inputs. But for now, I'll assume we have a real output, right? Sorry, not input, output. So we have a real valued output. Okay. So that's the setup that I'm going to work with, right? And now the first thing is that I need some training data, right? So I've been given some training data. So as I had said, that there are capital N pairs of, now this is a good notation, capital N for the number of training pairs and small n for the number of inputs that I have. The small n is equal to 1 in this case, right? So this is the training data that I have. Now my training objective, as I said, is going to be that when I make predictions, and these are the true values and these are the prediction values, I want the difference between them to be as small as possible. So this is my difference function, and this I'm going to calculate over all the training points, take the average, and I'm going to define that as my loss function. And my objective is to find w and b, right, such that my loss function is minimized, right? So that's an English explanation of this entire expression written here. Minimize with respect to w and b, which means find the values of w and b, which minimizes this quantity. And this is how this quantity is defined. It's the average difference of the predictions from the true values for all the training points, right? So that's a clear notation, right? Now, suppose I was given only 2 training points. Okay, these are the 2 training points given to me. These are the x's and these are the y's. So this is one x1 comma y1 pair, and this is the other x2 comma y2 pair. I'm just given 2 training examples, okay? And these are the values also, right? I mean, these are actual points on the graph. So I can see that one point is 0.5 comma 0.2, right? So this is the point 0.5 comma 0.2, as you can see. And the other point is 2.5 comma 0.9, right? So these are the points which are given to me. Okay, this is my input training data. And using this data, I want to learn W and P. Okay, that's the setup that I have. Okay. Now, what is happening? So at the end of training, we expect to find the optimal values of W and B, right? What are the optimal values? Though these are those values which minimize the loss function that we had defined in the previous slide, right? So those are the values that we want to find. So now what do you expect, right? So suppose at the end of training I told you that I've found W star B star. What is it that you expect? What would happen? I'll ask a more specific question. If I plug in the value 0.5 here, if I pass 0.5 as the input, and if you have learned W and B well, what do you expect to happen? The output should be close to 0.2. Similarly, if I plug in the value 2.5, I would want the output to be close to 0.9. Right? This is what I expect to be, and this is what I've written here. Right? So if I plug in f of 0.5, then it should be as close to 0.2, right? Tending to 0.2, and f of 2.5 should be as close to 0.9. Right? Now let's try to relate this algebra to the geometry. Right? So now geometrically, I know that I'm looking for a sigmoid function, which is a S-shaped function. Right? Now algebraically, what I'm telling you is that when I plug in these values, they should be as close to 0.2 and as close to 0.9. So now can you tell me what is the geometric interpretation of that? I'm going to get some function because this actually defines a sigmoid function, right? And now I've found some W and B, so I'm going to plug in those values, right? And then I can draw that function. So what should that function look like? Or what should be a characteristic of that function? Of course, it will be a sigmoid function. Of course, it will have S-shaped, but with respect to the training data, what should happen? The 2 points that I have shown here should lie on the function, right? So what that means is, let me just draw it. Lie or close to that function, right? So I'm assuming it's perfectly done. So this is what should happen, right? So whatever W comma B values I have, when I plug them here, I know that when I plug in the value 0.5, I want something which is close to 0.2, right? I'm drawing the best case here, that I should get a sigmoid function such that these 2 points lie on that. And that's what it means, right? That when I plug in the value of x, I get this y. When I plug in the value x2, I get the other y, right? So this is what we are looking for, right? So this connects, I would say, the math to the geometry, right? So the algebra to the geometry, that when you plug in these values, you get some output, and this is what it would mean geometrically, right? Okay. So now let us see this in more detail, right? So as usual, I never know what the W's and B's are, right? I've given these 2 points. I'm going to start with some random W's and B's, right? So here I have started with, if you can't see it, let me just see if it's on the file. So W equal to 3 and B is equal to -1, right? That's what I have started with, okay? And now this is the sigmoid function that we get. I know that, intuitively I know that this is not correct. Why is this not correct? Both the points are not on the function, right? This point is also not on the function, right? So both the points are not on the function. And just on the previous slide, we saw that when the network is trained, or when I have learned the values of W and B, I would expect these points to lie on the sigmoid function. But right now, it's clearly not the case. So this is bad. There is no argument about that. But how bad is it? Can you quantify that? All of you are saying that it's bad, right? That's a qualitative answer. Can you quantify that? Yeah. Right. So the answer given is that we could look at the loss function, right? So we now, what we'll do is that we'll look at the loss function, which depends on W and B, and we'll see how to calculate the loss function. And then we'll be able to say exactly how bad this is, right? So let's do that, right? So my values of W and B I know are 3 and -1. So I know that this is equal to 1 over 1 plus e raised to minus of 3x plus b, and b I have chosen as -1. So this is what my function looks like. Now in this function, I'll plug in all the points that I have. How many points do I have? Only 2 points. So for 1 point, the value would be, the x is 0.5 and the other x is 2.5. So I'll plug in these values and I'll be able to compute this quantity. And I already know what the true y should be, right? So I can calculate this. So I'm just going to go ahead and calculate this, right? So this is what it looks like. Okay, I've just expanded the sum. Now I'm going to calculate those values, and this is what the values turn out to be. Now I'm just going to do the math, and this is the value, right? So this is 0.099, that's the loss. If it was perfect, the loss would have been 0, right? But this is 0.099. So that's how bad this is. Now I am able to quantify my answer using the loss value. If you give me a W comma B, I can tell you how bad that is, right? That's what I'm able to do, right? Now we want the loss to be as close to 0 as possible. Ideally 0, but as I said, I would settle for approximately 0 also, right? So that's what we want to do. So let us try some other values of W comma B, right? And we'll use the slider to change it. Okay, so first I'll try, let me just see if I can do that. So first I'm going to try W is equal to 0.5. Okay, this is 0.5 and B is equal to 0, right? So let me just, for some reason I'm not able to change it. Okay, so suppose I do W is equal to 0.5 and B is equal to -1, right? This is also bad. And how bad is it? It's saying it's 0.121, right? So earlier my loss was 0.09. Now my loss is 0.121, right? So it's even worse, right? And you can see from the figure also that's even worse, right? So let me try something else. I'll try -0.1 now, okay? Like some of these values are not here, but let's say I try this value, right? Again, I see that my loss is increasing. So then I keep changing, right? So I keep trying different values, and then I tried 0.94 and -0.94, and I saw that the loss is 0.0214. Okay, so this is good. Okay, this seems to be good. So let's see what my rationale was, right? It started with 0.50, I got a loss of 0.07. Then I randomly jumped to some other point, the value increased. Okay, so then I concluded that I made the W negative. Maybe that's a problem, right? This is what my thinking was, right? This is how I've come up with these numbers. So let me increase the W. So I increased the W and I made B a bit negative and the loss decreased. Okay, so then I assumed, okay, increasing the W further and decreasing the B further might help, and that actually helped. And I kept continuing that way and it helped, right? I'm doing random guesswork, but it's slightly not so random because I'm looking at the loss values and slowly trying to adjust the weights, right? And all these values that I had tried, these are all the different functions that I got, right? So you can see what had happened for W equal to 0.50. You can go back and look at all these values. So I was getting different functions, and then as I kept changing it, I somehow found the right function, right? So this is what my guesswork was. And you can all imagine that this guesswork could have possibly never ended, right? These are very specific values, and I chose them because I knew what the right value was and I was just trying to get that. I mean, I've reverse engineered these. But if I was completely randomly trying this would not really converge, right? I would not end up anywhere, right? So now let us look at something better than this guesswork algorithm, right? So this is slightly better than the guesswork algorithm. So what I've done here is, again, we had seen this earlier. So I've just plotted. So this is my W axis, this is my B axis, okay, and the vertical axis is the error axis, right? So for all possible values of W and B, I have just computed the loss. I can do that programmatically, and I have just plotted it, right? And this is what the plot looks like, okay? And you can see that there is this region here where the loss is low or minimum, right? And there are certain regions where the loss is very high, right? So I could just plot this, and then I could just pick up some value from this good region here, and that would what my answer be, right? And we had seen a similar argument when we were doing the perceptron algorithm, and we need to know the fallacy of this argument also, that this is okay for this toy example, but it will become intractable as the number of data points increasing, right? So as the number of data points increases, just computing this loss would be very difficult for all the infinite values of W and B, right? And here, although I'm saying infinite, I've actually plotted this only for -6 to +6, right? Those are the only values. I'm not really plotting, I cannot plot for -infinity to infinity, right? So what if there was a value here, right, going forward this side, for which the loss was even lower? Right? So why I could have chosen that also, right? So this kind of just plotting the error surface and looking at it and figuring out the value, that does not work in practice, right? I mean, although this is a good way of seeing what is happening, you cannot do this in practice, right? You won't be able to get anywhere, okay? So now let us, with that plot in mind and my guesswork in mind, let us try to look at the geometric interpretation of what was happening in my guesswork algorithm, right? So we'll try to do that, okay? So what had I done? I had initially chosen 3 and 1 as my values, right? And then 3 and 1, or was it 3 and minus 1, I guess, right? So 3 and minus 1 is what I had chosen, right? So this is where I was on the loss surface. This is my 3 comma minus 1 point, and my loss was very high, right? And then from there, I randomly jumped to this point 0.5 comma 0. Right? And before I click enter, just see that when the value of x w1 w and b is 3 comma minus 1, this is what the sigmoid function looks like. And it's obvious that the error is high because it's nowhere close to fitting the 2 points that I have, right? So then I tried 0.5 comma 0, and let's see what happened. Now if you look at the sigmoid function, it looks a bit more favorable, right? And you can see that the loss has also decreased, right? But since I was randomly guessing, I did not have this error surface in front of me. So I just continued randomly, right? And then I went to the point minus 0.1 comma 0, okay? And I goofed up. You can see that I actually went up on the error surface, right? So I was somewhere, yeah, I was somewhere here, and I climbed up on the error surface, right? And then I changed it further. So what I did is, yeah, then I changed it to a 0.94 and minus 0.94. And then the loss decreased, right? And I can see from the sigmoid function also that I'm going in the right direction. And then I kept continuing in this direction, but you can see that my movements, if you look at the WB plane, they're very random, right? I was jumping from one point to another and just getting lucky somewhere. And once I hit this point 0.94 minus 0.94, then I get a sense of what is required. I need to increase the W's and decrease the B's. And then I continued that way. And then I finally reached to the point 1.78 comma minus 2.27, where my error was close to 0, and you can see that the sigmoid function is in the way it should be, and you can see on the error surface also I am in that low error region. In fact, the error is actually 0, right? So that's what I was doing. I was actually subconsciously, or like without really knowing it, actually navigating the error surface. But I was navigating it randomly, which is problematic, because then I went down, then suddenly I came up, then again went down, came up, and I want to avoid that. I want to have a more principled way of navigating this error surface, right? So that's what my quest is, and that is what we will do in the next module, okay?